Hello, this is Dr. Amudapriya, Associate Professor Triply from Rohini College of Engineering and Technology, Palkulam. We are discussing about the transmission and distribution subject for the Regulation 2021. Now we are going to discuss about the AC and DC distributions. While considering an AC distribution line with a singly fed line here being represented as ACB. Here let us have a feeding point A, and we are tapping the voltages or current from the point C and the B. Here we can see the impedance of section AC is R1 plus JX1 and impedance of section CB accordingly R2 plus JX2, and the current I1 and I2, they are having a power factor of 5:1 and the lagging power factor. So obviously ICB, which is going to be I2, and then IAC, which is going to be I1 plus I2. We are getting this equation. Finally VCB voltage drop is nothing but ICB into ZCB, and VAC is equal to IAC into ZAC. When we are substituting, we used to get VCB and VAC. Now the sending end voltage VA is nothing but VB plus VCB plus VAC, and the current IA is equal to I1 plus I2. This is how we are going to calculate for the AC distribution line. Regarding the phasor diagram, let us have here, you can see at B the consumer is tapping the current. So let us take the VB value as a reference. So while considering the phasor diagram, let us take VB as the reference voltage. So at the point B, the current which is flowing is I2. So let us have the current I2 at an angle of phi2 from VB. And next, we are having resistance and inductance. So the resistance has to be drawn I2R2, that voltage in phase with the I2, and from which at 90 degrees we used to draw I2X2. Now we are going to add this section. So what we are going to get is the point BC, the voltage at point BC. So now we have got VC. At VC, we are having a current called IAC. IAC current is obviously no. Yes, we are having VC here, and the current which is going to flow is IAC. So this IAC is being drawn at an angle of phi. Yes. So now this IAC is going to be flowing through the section AC, and here we have a resistance R1 and inductance X2. So let us draw IAC R1 in phase with IAC, and at 90 degrees we can draw IAC X1. By adding these three components we get voltage VA. Obviously voltage VA will be in phase with the, it is having a current of I1 which is at an angle of phi1. This is how a phasor diagram has to be drawn, and in this the voltage drop in section C1, CB, how it's calculated, and the point C we have to calculate it accordingly, and then we are in need of the I1 current, calculate that I1 current, and IAC is nothing but I1 plus I2. While adding, we are getting this voltage drop in section A, and finally voltage at A is nothing but the addition of VB plus voltage drop at CB plus voltage drop at AC. This is how we calculate in case of AC distribution. For DC distribution also we are going to calculate in the same way. Procedure is the same, except that we are going to have only the resistance here and not the inductances. So here we are having various different types, namely distributor fed at one end. Here we can see from the diagram the feeding point is only at A. So you are having a total, the total current is going to flow from A. It is getting tapped at C, D and E, and finally the point B is left. It is an end point. At C we have I1, at D at I2, and then at E we have I3. So the total current which is flowing at AC is nothing but I1 plus I2 plus I3, and after that at CD it is I2 plus I3, and at DE it is I3. This is a normal, general and simple distributor. Next, while considering the distributor which is fed at both the ends, at A as well as at B, we have three tappings, namely C, D and E. So there is a current flow from both the sides, and partially, I mean, if the voltage at end A is greater when compared to voltage at end B, obviously a higher current will be flowing from A than B. We have to find out the minimum potential point. Similarly, if suppose the voltage at B is greater than the voltage at A, more current will be flowing at B when compared to A. This will be the cases when both the ends are being fed with different voltages. If they are fed at both the, I mean, same voltage is being flowing through, then we can find out the minimum potential as per the current which is being tapped from each point. If it is tapped more at left hand side, then less amount of current will be flowing from the other side. Likewise, let us see. And next is the distributor which is being fed at the center. If it is fed at the center, obviously depending upon the load preferences, we will be providing the supply on the left side and the right side. If suppose it is a ring main one, that is if we have a closed ring type, then we will have a feeder at A which is being supplying at both the sides, clockwise and anti-clockwise. Here as per the tappings, we can have the current flowing through and the voltage drop accordingly. Let us consider this first one. We are having feeder at A. So the current from feed point A, since we are having 4 tappings, we have I1 plus I2 plus I3 plus I4. So the current in section AC will be the addition of all the 4. Current in section CD will be the addition of the rest of the things other than I1. And current at section DE is I3 plus I4, at EF is I4. So therefore the voltage drop, here we consider the resistance at the first section to be R1 and next is R2 and the other one is R3 and R4. So in order to calculate the voltage drop, you are just multiplying as per Ohm's law. And finally the total voltage drop is nothing but the addition of all the voltages. This is how we are going to happen in case of a concentrated load. Concentrated load in the sense I1, I2, I3, I4 will be different. So this is the case. Next is uniformly loaded distributor. Uniformly loaded distributor in the sense all the consumers will be consuming the same amount of current. So in such a cases, we can directly go for a total voltage drop equation. V is equal to from 0 to X. X is nothing but, let us consider a point C here for the, while seeing the second diagram. There is a point C which is at a distance of X and we are going to consider a elementary section of dx. In this case, it is 0 to X. I into R, depending upon the length, it is L minus X into dx. So you can apply the integration rule and then we'll get the value of IR into Lx minus x square by 2. The voltage drop over the distributor, AB distributor will be, we are going to consider X value to be equal to L. Obviously it is IR into L minus L square by 2. So this is how we are getting I 1 by 2 into IR into L square. Separating it, I into L, it is the total current I, and R into L, it is the total resistance R. So voltage drop is half I into R. Next is the feeding point is at both the ends, but we are having the same voltage. So this is what is going to happen. In this, we can obviously tell that the minimum potential point will be at the center point. This is a guess. So we can have it. If suppose it is I3, the current tapped at the center point, it is I3 is equal to X plus Y. That is, from both the ends, the current is coming. So the minimum, how you are going to calculate the minimum potential point? You are going to apply the mesh analysis rule, obviously. So what it is, voltage drop between point A and B is equal to voltage drop over AB. So it is V minus V. So V minus V is equal to IA into RAC plus IA into I1 into RCD plus IA minus I1 minus I2 into RDE plus IA minus I1, I2 minus I3 into REB. This is what is the case when the voltages are the same. If suppose the voltages are different, obviously the voltage drop over AB will be equal to V1 minus V2. I mean the difference, not the subtraction, it is the difference, V1 minus V2. And next we are considering the uniformly distributed load when it is fed with the same voltages. Then the current supplied from each feeding point is IL by 2. It is, so the current is current at point C, we can consider it to be IL by 2 minus I into X. So the voltage drop will be from 0 to X, IR into L by 2 minus X into dx. So this is the differentiation we are getting, and this is the voltage drop. Integration we are getting, and this is the voltage drop. Suppose we are having a maximum voltage drop, means that point will be L by 2. Uniformly load fed at both the ends with the same voltage. So it is L by 2. So on substitution we get maximum voltage drop is equal to 1 by 8 into I into R. In case of assembly fed at 1, it is IR by 2. Here it is IR by 8. So the minimum voltage is nothing but V minus IR by 8 volts. Suppose if they are fed with the different unequal voltages, then obviously we have it, because we have to separately find out for all the sections. So voltage drop in section BC, and then at point C how it is, and after that we have to calculate for the value of VA, VB, come across it. So on solving the equation we get X is equal to VA minus VB by IRL plus L by 2. So this is how we are getting the equation. Thank you.